everyone and welcome to Transformers course. In the previous video we covered the transformer efficiency. We are still in the transformer performance, so in this video we are going to cover the voltage regulation. Let's start. I will start by this question. What is the voltage regulation? Or what is the meaning of the word voltage regulation? To understand the concept, let us illustrate this simple example. We have a battery is going to feed a lamp, and the battery is connected directly to the lamp. So the voltage of the battery is 220 volts, and the voltage now applied to the lamp is 220 volt, which gives a full brightness for the lamp. So virtually there is no cable resistance, no significant voltage drop between the battery and the lamp. And the lamp receives the full supply voltage, which is 220 volt. What will be the case if we inject a longer cable between the battery and the lamp? Look for this picture. So any cable has a resistance. When a current flows, there is a voltage drop. As a result, the voltage reaching the lamp is lower than the rated value, which is lower than 220 volt. Since the lamp receives a lower voltage, its brightness will be lower. Look. So what is the solution to compensate this effect? Look for this picture. So the solution, or to ensure that the lamp receives a required voltage, which is 220 volt, we need to increase the source voltage, for example, something like 245 volt or 240 volt. The extra voltage offsets the voltage lost in the cable. Hence, the voltage at the lamp terminals becomes the rated value, which is 220 volt, and now it becomes or returned back to the full brightness. We can call it the voltage regulation percentage. This represents the basic idea of the voltage regulation. The difference between the source voltage and the load voltage, i.e. the drop, with respect to the load voltage, is called voltage regulation. Let us apply this concept to the transformer, and we need to answer these two questions. Can a transformer keep its secondary voltage at the desired level under different loading conditions? So the answer could be yes. When it will be yes? So when we are going to run this transformer at no load. So the source voltage equals the load voltage, where the secondary current is zero. But normally the transformer is not operating at no load. The transformer is operating at a specific load or under loading condition. So the answer is no, where the full load voltage or load voltage is lower than the no load voltage, and in this case we are going to have a voltage regulation. And that one leads to another question. Why does the secondary voltage of a transformer drop when a load is connected? Because the transformer has impedance, R equivalent and X equivalent, and that one causes a voltage drop within the transformer. But the answer as well can be yes. So how come that if we're going to increase the source voltage to compensate or to offset the effect of the drop voltage inside the transformer, so we can have full load voltage equals no load voltage. But in this case we have a voltage regulation because the primary voltage is increased rather than the rated value. So what is a transformer voltage regulation definition? As we can see here in the left side, we have a transformer connected to a primary voltage V1, while the secondary has no load, so the no load current is zero, and the terminal voltage between these 2 points is the no load voltage. While on the right side, we have the same primary voltage V1, and the load takes full load current, so the voltage between these two terminals is full load voltage. So what is the definition? Transformer voltage regulation is a measure of how much the secondary terminal voltage changes when the transformer goes from no load to full load, while the primary voltage remains constant. Mathematical wise, percentage of voltage regulation equals the magnitude of no load voltage minus the magnitude of full load voltage with respect to the magnitude of full load voltage multiplied by 100. We can observe from this equation that voltage regulation can be positive or negative depending on the power factor of the load, lagging or leading, and the values of the transformer's resistance and reactance. We are going to prove that one mathematically and using the Phasor diagram in the further slides. For ideal transformer, the voltage regulation is 0% because the impedance of the transformer is neglected, while in reality or practice, good transformers, they have a voltage regulation within 2% to 5% because R equivalent and X equivalent are counted. Before we start the mathematical analysis of voltage regulation, let me remind you about the Phasor diagram of passive elements. So if we have a resistance R and there is a current I going through this resistance, the voltage across the resistance will be in phase with the current. Look here, so V and I are in phase. So that one is a unity power factor case. The angle between V and I is 0. If we have a pure inductance L and there is a current going through this inductance, so the voltage across the inductance follows the equation L di by dt. If the current and voltage are sinusoidal, so the current lags the voltage V by 90 degrees. Regarding the capacitor, if we have a pure capacitor like this one, and there is a current I going through this capacitor, so the voltage across the capacitor equals 1 over C integral I of t dt. If they are sinusoidal, so the current I leads the voltage by 90 degrees. What will be the phasor if we have RL circuit as shown in the figure? We know that if we have a pure resistance R, the current I and the voltage across the resistance VR will be in phase. And if we have a pure inductance L, the current I and the voltage across the inductance will be 90 degrees apart, where I lags the voltage VL by 90 degrees. If we combine them together, the current I lags the voltage V by angle phi, where the voltage across the resistance R will be in phase in the current direction, and the voltage VL leads the current I, or I lags the voltage VL by 90 degrees. So we can make a projection here for VR, so V in total equals VR cosine phi and VL sine phi. So we can add them together. VR cosine phi plus VL sine phi will give us the voltage V in magnitude. Regarding the RC circuit, so if we have a pure resistance, the current and voltage are in phase. If we have a pure capacitance, so the current leads the voltage VC by 90 degrees. So in this case, if we have RC together, the current I leads the voltage V by angle phi. So we are going to apply the same concept. So in this case, VR will be in phase with the current I, and VC will be lagging the current I, or I leads that one by 90 degrees. So if we make a projection to the horizontal axis, VR cosine phi plus VC sine phi equals the voltage V. Let us take an exercise. We are going to extend the problem. Rather than we have one load, we are going to have RL load in series with another RL load. And this RL load has a voltage across that one will be V load, and the current going through this one is current I. So this means the current I lags V load by angle phi. We need to add the voltage across RL to find V supply. So what is the relation between what you explain and the voltage regulation? After this exercise and the next exercise, we are going to know what is the relation between what I'm explained or what I'm going to remind you by the voltage regulation. So let's look for this problem now that we have V load on I as shown in the figure. So I lags V load by angle phi. So we are going to have VR, which will be in the direction of the current I. So that one will be across the resistance R, and VL, where I lags VL by 90 degrees. So to have the supply voltage, we are going to add vectorially. So this means we have VR cosine phi, VL sine phi. So we can add that one where V load plus VR cosine phi plus VL sine phi can give us V supply. We are going to add them in magnitude. If we like to add that one as a phasor, we are going to see that one in the further slides. But in magnitude, we are going to make a projection for VR and VL in the same direction of V load, and we are going to add them together. So V load in magnitude plus VR cosine phi plus VL sine phi is going to give us V supply. Let us repeat the exercise, but in this case we have RC load. So this means the current I leads the voltage V by angle phi. We are going to add the voltage V load plus VR plus VL to have V supply. So we know that one is RC load and that one is RL. So in this case, we are going to follow the same concept. The current going through the resistance gives you a voltage VR will be in phase, and the current going through the inductance gives you a voltage where the current lags this voltage by 90 degrees. So look here, we have VR and VL. So we are going to make a projection for this one in the horizontal axis. So that one is going to give us VR cosine phi, and that one is going to give us VL sine phi. So we are going to add them vectorially to have the magnitude of the V supply. So VL plus VR cosine phi in this direction, and VL sine phi in this direction is going to give you V supply. So no wonder here that V supply could be lower than V load in this case, because we have a dominant capacitive load in the other side. So V supply could be more or lower than V load, and that one it depends on the voltage VR and VL in this case. Now it's time to return back to the transformer equivalent circuit to calculate the voltage regulation mathematically. So we are going to assume that the circuit is referred to the primary, and in this case we have V1 as a supply voltage, we have V2 dash, I2 dash, and Z load dash. we are going to assume a lagging power factor. So in this case, V2 dash and I2 dash has this phasor where I2 dash is lagging V2 dash by angle phi, and V2 dash is the reference with zero angle. We are going to use second approximate equivalent circuit. So in this case, I1 equals I2 dash. No need to use first approximate equivalent circuit as we concerned with voltages V1 and V2 dash. So we are not going to use no load current in these calculations. So we are going to apply Kirchhoff voltage law where V1 equals V2 dash plus I2 dash Z equivalent. If we succeed by any means to calculate V1 and V2 dash, we can calculate the voltage regulation, where the voltage regulation equals the magnitude of V1 minus the magnitude of V2 dash over V2 dash multiplied by 100. So this impedance R equivalent plus JX equivalent represents the transformer impedance, which causes the voltage drop. So we can say that V1 equals V2 dash plus the drop. If we succeed to calculate the drop, so we are going to calculate the voltage regulation where we can use this equation, drop over V2 dash multiplied by 100, or this equation if we know V1 and V2 dash. So the question now, how to calculate the drop? So when the current is going through the impedance R equivalent and X equivalent, there will be a voltage. Current going through the resistance R equivalent, there will be a voltage in phase with the current. Current going through the reactance X equivalent, there will be a voltage where the current is lagging by 90 degrees. Look, so that one is I2 dash R equivalent, and that one is I2 dash X equivalent. If we are going to add I2 dash R equivalent and I2 dash X equivalent to the endpoint of V2 dash, so in this case we can calculate V1 as a vector, or find V1 as a vector. So we are going to move that one in this direction where this part is parallel to this part and that one is going to be parallel to this one. So now we can have V1 where V1 has an angle delta with the reference 0. Usually angle delta is very small and V1 is the radius of a circle like this one. So our target is to calculate a point like this one. So our target is to calculate a point like this one. Or if we succeed to calculate this part, which represents the drop, so we can calculate the voltage regulation. So we are going to extract this triangular wave, and then we are going to calculate this part. So this is the angle phi, and if we have a line here, so that one represents phi as well. So we make a projection to the horizontal axis. So I2 dash R equivalent cosine phi, that one is the first vector, and the second one will be I2 dash X equivalent sine phi. So the drop is I2 dash R equivalent cosine phi plus I2 dash X equivalent sine phi. Now we succeeded to calculate the drop. The drop over V2 dash multiplied by 100 gives us the voltage regulation. So now we succeeded to calculate the voltage regulation for the transformer when the circuit is referred to the primary side with lagging power factor. So what is the voltage regulation if we have a capacitive load or a leading power factor? So still we have a circuit referred to the primary side and we are going to use a second approximate equivalent circuit. But the difference between this one and the previous case that we have a leading power factor now. So the voltage regulation is still V1 minus V2 dash over V2 dash multiplied by 100 or the drop over V2 dash multiplied by 100. So how to calculate the drop? This is a question. Now we have a leading power factor, so the current leads the voltage by angle phi. I2 dash leads V2 dash by angle phi. But this current going through the transformer impedance, which is R equivalent plus JX equivalent. When the current is going through the resistance, there will be a voltage in phase with the current. When the current is going through the reactance, the current lags the voltage across the reactance by 90 degrees. Look, so we have I2 dash R equivalent, I2 dash X equivalent. We are going to take these two vectors at the endpoint of V2 dash to find V1. So we are going to add them vectorially and we have V1 now. So that one is the radius of a circle like this one. So we are searching for a point like this one. If we succeed to calculate V1 now at this point, we can calculate voltage regulation or we are going to calculate the drop. So let us take the triangle away. So we have here angle phi, so we have angle phi on the other side as well. So projection to the x-axis, that one is going to give you I2 dash R equivalent cosine phi and I2 dash X equivalent sine phi. Please look for the arrows. They are opposite to each other. So in this case, we have the drop equals I2 dash R equivalent cosine phi minus I2 dash X equivalent sine phi. If we succeed to calculate the drop, so in this case we have voltage regulation equals a drop over V2 dash multiplied by 100. And in a capacitive case or leading power factor case, you might find that V1 is lower than V2 dash. We're going to prove that one using numerical examples in the further slides. Let's look for the problem if we have a unity power factor. Still we have the circuit is referred to the primary and we have a second approximate equivalent circuit. The voltage regulation equals drop over V2 dash. So how to calculate the drop in the case of unity power factor? So we know in the case of unity power factor, I2 dash and V2 dash are in phase. So when the current I2 dash is going through R equivalent, gives you a voltage will be in phase with the current, and I2 dash X equivalent, the current lags by 90 degrees. Look here, I2 dash R equivalent and I2 dash X equivalent. We're going to move that one to the other side and add it to V2 dash. We're going to have V1. So we are going to calculate the drop at this point where the drop is I2 dash R equivalent. Very simple. Because the angle phi is 0, so cosine 0 equals 1 and sine 0 equals 0. So the inductive drop will not be calculated or counted in this case. So the drop to calculate the voltage regulation is I2 dash R equivalent over V2 dash. That one is going to give us the voltage regulation. What will be the case if the circuit is referred to the secondary? We are going to apply the same concept, except that the current will be I2 and the voltage V2, and the voltage of the primary referred to the secondary side will be V1 dash. So the voltage regulation will be the magnitude of V1 dash minus V2 over V2 multiplied by 100 equals drop over V2 multiplied by 100. So what is the drop? So based on the voltage equation or the Kirchhoff voltage law, V1 dash equals V2 plus I2Z equivalent. So the drop is I2Z equivalent. So in case of unity power factor, the drop will be I2 R equivalent. And in the case of lagging power factor, so we have the drop I2 R equivalent cosine phi plus I2 X equivalent sine phi. For the leading power factor, we have I2 R equivalent cosine phi minus I2 X equivalent sine phi. So what is the difference between this case and the circuit referred to the primary, R equivalent and X equivalent? So R equivalent in this case will be R1 dash plus R2, and the X equivalent will be X1 dash plus X2. While the circuit referred to the primary, R equivalent is R1 plus R2 dash, and X equivalent will be X1 plus X2 dash. Let us summarize how to calculate the voltage regulation if the circuit is referred to the primary side or secondary side. If the circuit is referred to the primary side, so the voltage regulation is V1 minus V2 dash over V2 dash multiplied by 100, the magnitude of the voltage V1 and V2 dash, or the drop over the magnitude of V2 dash multiplied by 100. So what is the drop? I2 dash R equivalent cosine phi plus or minus I2 dash X equivalent sine phi, plus if it's lagging power factor minus if it's leading power factor. If it's unity power factor, cosine phi equal 1 and sine phi equals 0. So the reactive part is 0. So what is R equivalent? R1 plus R2 dash, and X equivalent equals X1 plus X2 dash. In case of the circuit is referred to the secondary, we have the voltage regulation is V1 dash magnitude minus V2 over V2 multiplied by 100 equals drop over V2 multiplied by 100. So in this case, drop equals I2 R equivalent cosine phi plus or minus I2 X equivalent sine phi, plus for lagging power factor minus for leading power factor. If it's unity power factor, so the drop is I2 R equivalent. Again, R equivalent here equals R1 dash plus R2, and X equivalent equals X1 dash plus X2. So far we know how to calculate the voltage regulation at full load. And we have the Kirchhoff voltage law equation, V1 equals V2 dash plus I2 dash Z equivalent if that one is referred to the primary, or V1 dash equals V2 plus I2Z equivalent if that one referred to the secondary. So the term is I2 dash Z equivalent or I2Z equivalent represents the drop. And we calculated the drop as I R equivalent cosine phi plus or minus X equivalent sine phi. And we said positive for lagging power factor, negative for leading power factor, and I depends on the referring of the circuit. So that one could be I2 dash or I2, and R equivalent and X equivalent will be R1 dash plus R2 or R1 plus R2 dash. It depends on the referring. So how to plot the loading characteristics? As we are going to increase the load current from no load to full load, or percentage of loading from 0% to 100%, we are going to have these loading characteristics. So the blue one will be the inductive load, the red one will be the resistive load, and the green one will be the capacitive load. As we can see here at this point where X equals 0% or there is no current in the secondary side, so the load voltage equals the no load value, and in this case voltage regulation will be 0. As you are going to increase the loading or the percentage of loading up to 100%, you are going to have a voltage regulation at this point, where the voltage at this point minus the voltage at this point over the voltage at this point gives you the voltage regulation, which is V1 minus V2 dash over V2 dash multiplied by 100, or the drop over V2 dash multiplied by 100. If that one is referred to the primary, if it's referred to the secondary, will be the drop over V2. As you are going to move from resistive load to inductive load, you are going to have more voltage regulation at this point. And if you are going for the capacitive load, don't forget this sign will be negative, and sometimes we have X equivalent sine phi will be more than R equivalent cosine phi, and the drop will be negative in this case, and here we can have a negative voltage regulation. So voltage regulation could be positive, could be negative. It will be positive if it's resistive load or inductive load, and if it's capacitive load, it could be positive or negative. It depends on the value X equivalent sine phi compared to R equivalent cosine phi. It's about time to have an example now. So this is example number 6 in video number 6. We are going to repeat it here to calculate the voltage regulation. We have a 10 kilovolt ampere, 2000 volt / 200 volt, 50 hertz step down transformer. We are given R1, R2, X1, X2, and also we have information about R core and XM. So this means we are going to use a first approximate equivalent circuit. But in voltage regulation, you didn't calculate anything using the first approximate equivalent circuit. We are concerned by the voltages V1 and V2 dash. If we are going to calculate efficiency, we need the first approximate equivalent circuit. But when we are going to calculate the voltage regulation, we need to know the values V1 and V2 dash. So what we need to calculate the primary voltage, the voltage regulation, if the load has 0.8 lagging power factor and the secondary load voltage is adjusted to 200 volt. So this means this voltage, when will be referred to the primary, will be 2000 volt, and we are going to choose that one with angle 0. Also, what will be the voltage regulation if the load is unity and leading power factor? Let's start. If we return it back to example number 6 in video number 6, we have the turns ratio equals 10, R2 dash equals 4, X2 dash equals J8, and V2 dash equals 2000. We are going to choose that one with 0 angle. So I2 dash is calculated 5 angle minus 36.8 degrees, or equals in rectangular form 4 minus J3 ampere. If we're going to calculate V1 using Kirchhoff voltage law, so the primary voltage is V2 dash plus I2 dash Z equivalent, which equals 2080.34 angle 1.1 degrees volt. So what is the voltage regulation at 0.8 lagging power factor? We're going to use two techniques or two methods. Method number 1. Voltage regulation equals the magnitude of V1 minus V2 dash over V2 dash multiplied by 100. 2080.34 minus 2000 over 2000 multiplied by 100 gives us positive 4.02%. Method number 2, we're going to use a drop equation, where the drop equation equals I2 dash R equivalent cosine phi plus I2 dash X equivalent sine phi, plus because we are lagging power factor. All the information are here. So R equivalent equals 8 ohm, X equivalent equals 16 ohm. So the drop equals 5 multiplied by 8 by 0.8 plus 5 multiplied by 16 multiplied by 0.6 gives us 80 volt. So the voltage regulation is the drop over V2 dash multiplied by 100. 80 over 2000 gives us positive 4%. The results are matching. What is the voltage regulation at unity power factor? We are going to use a drop equation, where the drop equals I2 dash R equivalent cosine phi plus or minus I2 dash X equivalent sine phi. And at unity power factor, phi equals 0, so cosine phi equals 1 and sine phi equals 0. And we know R equivalent is 8 ohm, so the drop is I2 dash R equivalent equals 40 volt. So the voltage regulation will be the drop over V2 dash multiplied by 100 equals 2%. Regarding the 0.8 leading power factor, we are going to use the same equation, where the drop equals I2 dash R equivalent cosine phi minus I2 dash X equivalent sine phi. So R equivalent is 8, X equivalent is 16, so we are going to substitute in the equation, so the drop equals minus 16 volt. And the voltage relation in this case will be negative. So that one will be minus 16 over 2000 multiplied by 100, minus 0.8%. Let us summarize the three cases now for the power factor. When the power factor is 0.8 lagging, the primary voltage is 2080 volt and the voltage regulation is 4%. while for the unity power factor, it will be 2040 volt and the voltage regulation is 2%. In the case of 0.8 leading power factor, the primary voltage is 1984 volt, which is lower than the referred secondary voltage to the primary side, and the voltage regulation will be minus 0.8%. Let us take another example. A 2.4 kilovolt ampere 400/200 volt step-down transformer supplies a load operating at full load current. So the current I2 dash is at full load. And 0.8 power factor. I didn't mention lagging or leading yet. The equivalent resistance and equivalent reactance referred to the primary side are 0.8 ohm and 1.2 ohm, respectively. Assuming the primary voltage is maintained at 400 volts, so the primary voltage here is 400 volt. I don't know what is the angle of this primary voltage, so I'm going to choose that one delta angle. We need to calculate the voltage regulation at 0.8 lagging power factor. So now we know that the power factor is lagging. And what is the secondary terminal voltage? So the voltage here is the referred voltage to the primary side, but we don't know what is the value of this one. So definitely that one, something is lower than 400 volt if that one is fixed at 400. We are going to choose that the secondary voltage is 0 angle. So the angle between I2 dash and V2 dash will be the power factor angle. So if we succeed to calculate delta and V, we can solve the problem. So the problem looks easy from outside, but it's a bit harder from the previous example. So let's start. Given S equals 2.4 kilovolt ampere, the turns ratio 400/200 equals 2. We have R equivalent, X equivalent, and we have V1, magnitude of V1 is 400 volt. So we are going to use a second approximate equivalent circuit, so we need to calculate the full load current. We know the equation that V1 equals V2 dash plus I2 dash Z equivalent. So we know Z equivalent. We need to calculate I2 dash at full load, and we are going to substitute in this equation. So at full load, we have I1 equals I2 dash equals S over V1, because we know V1 now. So 2400/400 equals 6 ampere. What is the angle of this current? So the current angle is calculated based on the power factor. Cosine theta V minus theta I equals 0.8, and that one is lagging power factor, so the angle is minus 36.8 degrees. So the current I2 dash will be 6 angle minus 36.8 degrees ampere. The equivalent impedance is 0.8 plus J1.2, so we are going to put it in a polar form. That one will be 1.442 angle 56.3 degrees ohm. Now we can substitute in this equation where V1 equals V2 dash plus I2 dash Z equivalent. We know V1 magnitude, which is 400, but we don't know the angle delta. We know for V2 dash the angle is 0, but we don't know the magnitude. So 400 angle delta equals V2 dash angle 0 plus 6 angle minus 36.8 degrees multiplied by 1.442 angle 56.3 degrees. Let us rearrange this equation. So 400 angle delta equals V2 dash angle 0 plus 8.652 angle 19.5. So we have two unknowns here in this equation, delta and V2 dash. So how to solve this equation? We are going to make a projection to X and Y direction, or we are going to take the cosine and sine. So 400 cosine delta equals V2 dash cosine 0, which is 1, plus 8.652 cosine 19.5. So we are going to solve this one. So 400 cosine delta equals V2 dash plus 8.156, and that one we call it number 1, equation number. Let's take the sine. 400 sine delta equals sine 0, V2 dash sine 0 is 0, plus 8.652 sine 19.5. So we are going to solve this equation. So 400 sine delta equals 0 plus 2.89. Call this one number 2. Solve number 2. We can find delta. Delta equals 0.414 degrees. Let us substitute in equation number 1 to find the magnitude of V2 dash. So V2 dash equals 391.83 volt. Now we can calculate the voltage regulation, which is V1 minus V2 dash over V2 dash multiplied by 100. And that one gives us plus 2.1%. Can we simplify the problem? Yes. We are going to assume angle delta is 0, because that one is 0.414, so very close to 0. But if the angle delta has appreciable value, so it's recommended to use the previous method. But now we are going to assume angle delta is 0, so we know the equation V2 dash equals V1 minus drop. And the drop equals I2 dash R equivalent cosine phi plus I2 dash X equivalent sine phi. We know the magnitude of I2 dash, we know R equivalent, we know X equivalent. Cosine phi is 0.8, sine phi is 0.6. If we substitute in this one, we are going to have the drop equals 8.16 volt. And in this case, V2 dash equals 391.84 volt, which is pretty close to what we calculated in the previous methods. So in this case, the voltage regulation will be plus 2.08%. So what is the secondary voltage now? We are going to use the Turner's ratio, V2 equals V2 dash over A. In this case, instead of 200 volt, will be 195.92 volt. So to keep the supply voltage or the primary voltage 400, the secondary voltage will drop from 200 to 195.92. But if you like to keep the secondary voltage 200 volt, you need to elevate the primary voltage more than 400 volts. What is the transformer loading characteristics at different loading conditions? For example, number 13, I built for you a MATLAB code or M code, shows here that we have the current changing from 0 ampere up to 6 ampere. And what is the load voltage at unity power factor, 0.8 power factor lagging, and 0.8 power factor leading. Definitely you can build that one at different power factors, but that one just an example for 0.8 lagging and leading and unity. So here we have the red color represents the unity power factor. As you are going to increase the current, we have a drop in the voltage. We can reach up something like 395 volt. That one is referred to the primary. And if you have inductive load, so we can reach something like 391 volt. But for the capacitive load, that one is more than 400 volt. So the voltage is increased. Regarding the voltage regulation, so here if we have the unity power factor, which is the red color, so we might reach something like 1.5% in the full load, but at zero load we have 0 voltage regulation. As you are going for the inductive load, so which is the blue color, we are going to reach something like 2.08%. Regarding the capacitive load, that one is negative, below the 0. Exercise. Repeat the previous example, but this time calculate it for 0.8 leading power factor and calculate the secondary terminal voltage. But you calculated that one and you showed that one using the M code. Yes, but you are going to prove that one analytically. Make sure that the voltage referred to the primary V2 dash will be more than the primary voltage, more than 400 volt. And also the voltage regulation will be negative. What will I watch in video number 9? In video number 9, we are going to cover the transformer testing. See you in the next video.